I can't look at this. Okay, I've just spent and this. Let's see that like 4 hours cutting and chopping away at this video I just made because I kept making all these mistakes, and now there's so many different branches and variants that I don't know how to put it back together again. So I'm going to do the whole thing over from scratch. Goodbye. Goodbye. How come I can't delete? Delete. Yeah. And this why I want this either. Alrighty then. As indicated by the title of this video, I have done actually this you know when I started this? It was midnight, just after midnight when I started this, and I was surprised that I had fallen asleep and a whole day had gone by. Now here I am and it's almost 7 in the morning, and I'm going to do it again. This should be quite easy. The title of this video should be saying how to read symbol files or something to do with symbol files, which is what the other thing that I figured out yesterday, or last night, when I didn't have any internet. Okay, now in order to aid me in this thing, besides the aid that I've received already from the Debug Help library, well, actually I've had this class for quite a long time, but I just haven't really used it. So I did make some changes, and of course goofed up a few times. Now all this class is meant for is to manage working with that type of object, object type that you love and know and love to hate, the pointer to void. Pointer to voids don't point to anything, so it's always a hassle dealing with them. You know, it's hard to change the number value and so on. So this helps with that. It also has a few helpful functions with it. I like to check if a pointer is valid, like readable, if you can read the pointer. If you can read at least 4 bytes, because typically for this thing, it's an address, and we should be able to read at least 4 bytes worth of an address, right? Think of this thing as an address in memory. Well, it might be pointing to 1 byte, but usually the pointers that we're looking at are pointers to pointers, or pointers to pointers to pointers, and so on and so forth. So therefore, we need to be able to read at least 4 bytes. All right. Now let me I've actually modified this program about 12 times during this go, and I've re-explained various things about 3 or 4 times. But let me just show you one of the things that I can do now, just in my little unit test, which is a stack walk. Okay, so this is an example of a stack walk. And hopefully it won't crash. No, it didn't. Alright, now what this printout is showing us is the first thing I'm printing is the current address. Alright, now I'm using this is the same format the debugger uses. I run up to this point and look at what we call a call stack, what I'm trying to reproduce. This is the standard format, module name, exclamation point, and then name of function that we're in. Now, I can also retrieve these things the Debug Help library, but I haven't done that yet. And this here line, that's not the same as this 134. I put these ads in and I should remove them now. I put them in for another reason, which I may or may not be able to get to depending on how messed up this goes. This just means plus 134 bytes. So our current location is within utest module offset 1b06, which is in function main offset 134 decimal bytes. I had a problem with that too. This is in decimal. I should probably put it in hex because the rest of it's hex. But it turns out that normally people don't put these in hex. So I put it in decimal because that seems to be the tradition. The last little bit in square brackets is an indicator to me anyway of what I know about how this function got entered. I know that the best guess is that it got entered through either a call or a jump. I can actually determine which one of these it was by reading a little bit further back from where I believe the call was, my return address, and check to see if it's one or the other, but I'm not doing it. At some point, okay, if you're going back to this here, and you'll notice it gets gray here. See how it's gray here? The grayness indicates that, I believe anyway, because it indicates for me the same thing in my stack block, that at this point, after main, the last one here, this is all the same, the caller function, which I can figure out, I know it's this function, and that the name of that function I got out of the Debug Help library. It's not indicated here, but it's indicated here. This function, I don't know how this function got entered, right? So I'm unsure about the way in which this function got entered, and I would probably put it in a different color too. Because I don't know how this got entered, I don't know for sure how these others got entered either. But they're all on, if I'm walking the stack chain, which you do by taking the base pointer and dereferencing it over and over again, these are all in the list. Eventually I get the null when it stops. Those are in the list. So there are stack frames in the linked list of stack frames, but I don't know how did this function got entered. What I mean by not knowing is that each function has a return address. And here I go into my thing. I'm probably going to mess it up. But, oh, look, I still got some of it written. Okay, if if a function is called via one of these two methods, by using the call or jump instructions, then on the stack, which if you recall from DOS, the same in Windows, the stack contains a return address, right? Now that is pushed on the stack by the processor, not the operating system. And then if we're using the stack frame mechanism, for our code, then we say push BP or enter an instruction. It does this in a single step. This sets up the stack frame. So this is done immediately at the point of call. So the next thing on the stack following the return address is the EBP, the caller. The caller's EBP, if you like. EBP is called your base pointer and defines the stack frame. After that push here, the stack pointer is always pointing at the last thing that was pushed. Its value will be here, not for long, as you know. Following this is local variables, and on the top are arguments passed in. Right? Passed in. Just the wrong center. So arguments passed in. Args passed in. And here are local variables on the stack. And sometimes this pointers can go here, right? So to reference local variables, you subtract, now to get a pointer to one of these local variables or arguments passed in, we use our RBP. See, we have saved off in EBP and we've promised not to touch it, a value. And when I dereference EBP, right, it has the same value as ESP had at the point of call. So therefore, if I subtract numbers from EBP, I get local variables, and if I add numbers, I get arguments passed in. If I add 4, I get the return address, right? So that means that we use EBP to reference local vars and params and return address, right? EBP plus fx equals, plus 4 specifically is the return address. P itself is equal to the caller's EBP. That would be the stack frame of the caller. Plus or minus 4, either a this pointer or last local variable. Because the stack goes down. So everything's upside down with the stack. The first thing that you declare, what am I saying? First thing I declare, it depends. No, it's the first. Right? Because it grows down. So I get, the more things I declare, the further away things are. So it's either this pointer or but I'd have to say that it's the n as well. No, the reason I'm getting I'm not sure how to put it is because because of the thing about arrays. If you declare an array, right, on the stack. Suppose you add 10 to ESP to make an array. Then the first element of the array will be lowest in memory. So if I say, if I declare an array stack, then the first element of the array is lowest in memory, and so EBP minus the size of the array will give you the head of the array. So EBP, so to get the head of the array, we subtract array size from the thing that references it from the variable name, from the internal variable name that you never see. How about that? I don't know how to say it in words. When we subtracted from ESP to allocate the array, that value of whatever EBP was there is the one that we use to reference that array. Then we got to subtract the size of the array to get to the front. It's the first thing. So this is my function. And I say int I of 100, right? X. Then in assembler, that's subtract ESP 100, right? And then if I want to get I of 0, the first element, if it's int, to do this in assembler, I would have to say EBP minus 100. Because that's where the front of the array is. Front of the array is lowest in memory, if memory is increasing. So the start of the array is not EBP, but of EBP minus 100. Sorry. Now what was I trying to say? So this is what the stack looks like, and as I just said, we can use EBP to find out the callers or the return address for our function. Now, if the function was called, it would have used this mechanism. This applies both for a call or a jump. The instruction, the opcode. Sorry, this is wrong. The opcode is either an E8, which is a call, or E9, which is a jump. Alright? And then following that, one or the other of these two, is a 4-byte relative offset operand. This one's called the opcode. This one's should put it up here, shouldn't I? 4-byte relative offset. And this is just the size of the instruction. Okay, now, so that means that the instruction is 5 bytes, and what I've written here is that the way it works is, as far as specifying this relative offset, relative meaning that it can be, it's relative to the current location where the thing's going to jump call to. It's relative to the current location, and it doesn't make any sense to jump like into the middle of an instruction. So 0 means that to jump or call to current position plus the size of the instruction, which is 5. So offset 0 means go to instruction plus 5. So here, and so in general, the destination address is the instruction address plus 5 plus the offset, relative offset specified here. Maybe it's easier if I do it like that. 1, 2, 3. Is that 8? 1, 2, 3, 4, 5, 6, 7, 8. Oops. Okay. Alright, so therefore it's possible for one to determine where the start of one's function is, and you can do that by looking backwards, taking the return address out of the stack, and then subtracting 4, okay, from reading this value, okay, and then the place where this thing is calling to is worked out using this calculation, and so you can work it out quite easily. What the function is that you're currently in, given an EBP. And star EBP is another EBP, the caller's EBP, and if that's true, that's true of the caller, and so on and so forth, and therefore you can do this walk. Now, I've already said a lot, and I've done it too many times. So maybe what I'll do is this will just be an intro, and I'll try to make a nicer introduction to this section. Maybe doing another once over through this whole business with the stack and how calls work, and why, for instance, this is unknown, which the method. The reason why I'm saying this is unknown is because I can't read anything at the address determined using this calculation. If I go back, if I take this function, take its stack frame pointer, its EBP, and using that, find the return address, and I read in the instruction there, I don't get a valid. It doesn't call anything anywhere near anywhere. It just gives an invalid pointer. So, and I know the reason why in this case. The hint is that this is called a thunk. Okay. Now I don't know if this UNK stands like it's supposed to mean unknown, but that would be a good meaning for it. What these things are used for are entry points to getting into another function, let's say, where you don't want someone to know how you got there. You don't want it to be able to be traced back And that would be in the case where this is coming out of the operating system. The instruction pointer is wiggling out of empty kernel and into your program to start running. You're not allowed to trace back. And the way they do that is this function is a function, but it's not called. There's no call associated with the entry of this function. It's an address that is returned to from somewhere, and so therefore all information about how this thing got entered is gone, completely wiped out. If this has been returned to, so that address was on the stack, which is now been trashed by this time, because there's available memory, and the wherever its stack frame points to it's not a call instruction, so there's no way for us to trace it back and find out how this got entered. But we can still continue to walk the stack frame and come up with more functions. And these are the same functions as as much as the debugger can get out. We know that at this base thread init, we don't know how we got there, but we know what the address is. We can continue along the stack, the linked list, which the stack frames are in a linked list format. The next function at EB, that's this one. Now I'm saying you test, but I could work it out. I'm just doing this pretty cute. I have the module in my output. I have all of the loaded modules and their addresses, and I can work that out easily. Somewhere in here. See? This is my printer. And I can figure out from these numbers that this would have to be between here and here. I know all the modules loaded, and so I can find out which module this address is in. Okay. Now this is a little more information. Obviously, there's we're in the middle of a try, right? There's a try surrounding this code just by the name, initialize exception chain. So you can guess what that might be doing. Now, these are just offsets from that same initialize exception chain. Whether these are function calls or not is anyone's guess. This one appears to have been called from here. That's why I'm seeing an address there, but I'm not verifying for sure that everything adds up properly. So, but I could. And then we just get not printing the address, but there's another address here, and we don't have the symbol for it, so it doesn't really matter. But I'll print that out. But you can see how this is useful, combined with this new address class, which has the handy feature that the way I walk the stack frames is by specifying a bigger and bigger number for this U, get EBP, dereference, and it optionally takes a context. I think I mentioned that in the beginning. I can't remember now. If I didn't mention it, this PCONTEXT is supplied by the operating system, and in a situation where an exception has occurred, we are given a PCONTEXT, and we can use the same stack walker to walk an arbitrary context stack until we hit the end. And so that's what I'd like to do. And I'd like to do another once over with this. Okay. All right. See you.